All right, everyone. So hopefully everybody's having a good day and enjoying themselves. So I've been to a variety of talks today, and lots of the talks are on the cooler side of AWS. So looking at serverless, looking at some of the new data services, so Athena, Glue, and others, but very little talk about legacy. Lots of the clients that we work with at the moment still have large legacy services stuck in physical data centers. They have aspirations to move to public cloud, aspirations to move to AWS, but not sure how to do it for those legacy services. So in the next half an hour, hopefully, we're going to discuss some of the ways how you can make legacy legendary. So we'll briefly introduce each other, a brief history of how we got here, the problem statement, the platform that we've built, and then we're going to actually try and do 2 live demos. So hopefully the demo gods are with us today. So Indy, do you want to introduce yourself first?
Yep, hi. So I'm Indy Baines. I've been with Capgemini now for about 13 years, and most of that time has been in the infrastructure environment space. And over the last few years, we've seen a big shift from the way we worked previously with physical data centers, lots of siloed teams, to more modern ways of working on platforms, everything as infrastructure as code, and I've been helping drive that along over the last few years.
So I'm Doug Thomson. I work alongside Indy, again for Capgemini. If anybody wants to know more about Capgemini, we do have a stand next door, so please come and see us at any point. So before we go on, a couple of questions for you guys. So who here has used Docker? Quite a few, good. Who here has used Windows? Yeah, quite a few moans, okay. And who here has used Docker with Windows? Ooh, excellent, good. So a little bit of brief history, okay. So in September 26, Docker and Microsoft announced a partnership together. And what that meant was you could now effectively install the Docker engine within Windows 2016 without the need to buy a license or anything else, and you would get support from Microsoft for that engine. And then in April 2017, Docker announced something called the Mta Program. So Mta was all about modernizing traditional applications. So taking your legacy services, which are running in your physical data centers on out-of-support operating systems, and migrating them into containers. That then progressed in November 2018, where Docker launched a new program specifically aimed at Windows 2008. So with Windows 2008 end of life coming up soon, Docker have done a whole program around migrating 2008 onto 2016 or 2019-based containers. And their sales pitch is kind of around this diagram at the bottom here. So the ability to take existing applications, to modernize the infrastructure that they run on, to look at taking some modern techniques, so continuous integration, continuous deployment, automating the build of those containers without a single line of code change. So we looked at that and we thought, is that really possible? So we thought we'd have a go. So our client's challenge is, what do you do if you have a large legacy Windows 2003 estate and want to move to cloud? And what we're going to show you in the next probably 20 minutes now is one potential solution to do that. So we have built a large production-ready environment. However, a 20-minute demo doesn't really give it justice. So due to that, what we've done is we've built a cut-down version of that for the demonstration today. So everything is built using code. So we've used Packer to build AMIs. We've used Terraform to build our base infrastructure. Everything is highly available, highly resilient, and self-healing. So we've used the likes of auto-scaling groups, S3 buckets for certain components, elastic load balancers for load balancing our services. But rather than talk too much about the diagram, what I'd rather we did was just get down into the demos.
Okay, so So the first thing I want to show you is the application. So this is a .NET 2 application running in a container on Windows 2016 base image on Windows 2016 VM running in AWS. Now, the process takes a few minutes to build, so what I'm going to do, I'm going to make some code changes, I'm going to kick off the build, and then as that's building in the background, we can go through more details of exactly what's happening. So I have a number of files I need to change. So the first one I'm going to change is the source code to change the background color. So at the moment, it says it's pink, so we're in AWS Summit, so I'm going to change it to orange. And I'm going to commit this change. And what we should see in the background in a minute, a pipeline kicking off that starts to build that pipeline. While that's happening in the background, I'm going to go off and change the second file. That is here. Oh, I forgot to change something. Sorry, I forgot. Yep, so that's that one, and I need to go in and change web Docker file. I'm going to change a label value here. From 24, I'm going to change that to 25. And I'm going to also change this to be 25. Commit. And right, so as you can see now, on the right-hand side, we've got the first job kicked off automatically. And if you look at the logs, what this does is it uses a method called multi-stage builds, where if I go into the Docker file, I can show you, we have in this file 2 from statements. So what we do is we use one container that has all the build components in. So all the tooling that's required to build your application. We build all of our container images from source code. So we have full auditability of any source code change right the way up to it running in production. So the build container here has all the tooling required. Once the source code has been compiled and is ready to use, it is then moved across into the second container here, which is our run container. The difference between the two is our run container has only the components needed to be able to run the application, none of the supporting tools around being able to build it. So this adds an additional layer of security in case if our container got compromised for whatever reason, it's not possible to recompile the code in situ within that container, so it gives you that degree of security. So if I just got back into this one here, so what we can see, the container has been built automatically, and at the end of the last thing it does, it pushes our built container up into our container registry. So for this demonstration, we're using GitLab as the container registry as well, so it's self-contained. Other environments, we have different registries, such as DTR. On success of this pipeline, it then triggers an additional, the next step of the pipeline, which is the deploy. So if I just go into pipelines, we should see that one's running and has run. So what this does, it then takes the container that we've built, it then deploys this container into our environment. And the way we do this, so we wanted the platform to be very much self-service for our development team so that they can manage and deploy their own applications at their own pace. But we still needed some governance around it. So we implemented a mechanism where the teams themselves could implement their own metadata within the build stage and the definition that then triggers further downstream pipelines. An example of this is the version. So we take this version out of the Docker file itself, and that's the version of the container that gets pushed into the registry. These are immutable tags, so what that means is once you have a version .25, that will live for life. That you can't have another version that's .25. And we share the same registry between our production and our development environment, so we always have a single version of the truth between both environments. The development teams are also responsible for building, for writing the stack file, which is this file, and that is, if you're not familiar with Docker, this is how you define how multiple containers talk to each other within a service. So normally services consist of more than one container, and this is how you would define them. By changing the version of what images they're running and passing in certain parameters, the development teams are in control of their own deployment of the lifecycle, and they can do this at their own pace. The pipelines we have are also held within the same source code repository. So it always gives us at any one point an exact version of the source code and the pipelines that were built to build and deploy this service. Now hopefully if I refresh this page, we should see the color changing. So it doesn't take a few seconds, but this is still a Windows image. It's an IIS image on some old .NET technologies, but there you go. So it's changed, it's worked. All I did was make some code changes and commit the changes back into my repository.
So that kind of demonstrates how in about 3 minutes you can build an application on Windows, so an old legacy application on Windows, and you can also deploy it into AWS. So something that has taken 3 minutes that previously might have taken hours, days, weeks. This kind of approach, we've kind of proven it against a variety of legacy type applications. So providing you have the source code for your .NET applications, you can follow something very similar that then gives you a very consistent and repeatable build and the ability to deploy.
The other advantage of using the containers is whilst the application code is still the same, we haven't changed any application code. There are changes to configuration, but configuration is designed to be changed between different environments. That's the whole point of it. But no application code changes. We're allowed to then use modern tooling to manage and monitor how the application services run as well. So we've shown you how we can build and deploy a container using some modern tooling, but also how we can visualize it as well. So this is a tool called Visualizer. At its simplest, it just shows you what containers are running on what host. It gives you a very, very high-level view of what's running everywhere. We can use tooling like this. So this is Elastic with a Kibana dashboard. But what you can see here, we've got logs coming in from our Windows machines and also from our Linux instances as well. So we're using, to do this, Docker Enterprise Edition. And what that gives us, one of the advantages of that is it allows us to run dedicated Windows workers as well as Linux. And we also have a choice of orchestrator as well, so whether we use Docker Swarm or Kubernetes. So it gives us quite a bit of flexibility and lots of choice. We can then implement some other tooling as well, like this. So we've got here, this is a Grafana dashboard on top of Prometheus. And we can start to get some metrics now across all of our services, our nodes, how much CPU, memory, network I/O they're using. And that's in a single pane of glass view for us now. Across 2 different operating systems, potentially across multiple cloud providers, hybrid, on-prem, it doesn't really matter. But we get that single pane of glass view, and we can manage all our legacy infrastructure using some modern tooling.
But hold on, Indy, right? So this is the AWS Community Summit.
Oh, yeah.
So why don't we have a look at some of the AWS stuff? Yeah?
Okay. So this is AWS console. So you can see in here we've got some machines running. And so we've got, this is Elastic, and we've got some managers running. We've deployed this to make it highly available. They're running auto-scaling groups, and they're distributed across 3 availability zones. What that gives us is a highly available deployment. If anybody's deployed anything into an ASG, you realize that if you're deploying a cluster, it gets quite awkward. So what does the first machine that starts up, what does it do? Does it start up a cluster? Does it join an existing cluster? So we've had to build all this logic into our application. And what we're going to do now is simulate an availability zone failure. So let's grab a subnet. So if I grab that one, if I grab that subnet, filter on there. I've just got mine, that's probably a bad example. Let's pick another one.
You need one with the Windows worker.
Yeah, I'm just doing that one now, so let's have a look. Okay, so we've got 2 machines in there. And what I'm going to do is simulate an availability zone failure as dirty as I can, which is just to terminate those machines. So, if you imagine that, going back into our existing world where this is legacy infrastructure running, this application is running at the moment on physical tin. If we had a data center failure, it's not going to self-heal. But this is one of the advantages that we get when we do move into public cloud.
So can we first see that the application is still working?
Yeah, let's have a look. So I'm going to use, yeah, it still works.
Okay.
conference Wi-Fi is a little bit slower than what it normally is.
Okay, and then if we go back into UCP, we should see that some of those nodes are becoming unhealthy.
Oh, yep, there we are. So there you go. So that's one of our managers that's down. And if I hit refresh, we should see one of our Windows workers failing as well.
So the approach that we've used is to bake as much as possible into the AMI and also to follow the principle of run as much as possible in containers. So by running as many of the services within containers, it makes them portable and very, very quick to start. By baking everything into the AMI, it makes the auto-scaling group quicker to start up those EC2 instances again, yeah, or create new EC2 instances. So anybody who's ever tried to do config management on Windows will know that that can be some of a challenge. So certainly, again, from the Windows side, it generally takes a little bit longer for the EC2 Windows machine to start up. But what we should see within a couple of minutes is effectively we've spun up another master and another Windows worker, and that the container that was running our .NET 2 application will also get deployed onto that Windows worker.
Yeah, so that sounds easy. When we drew up on a whiteboard, we said this is what we want to happen. But in reality, it took a little bit of time. It's quite difficult to make things simple at times, which is weird. But we had to work out, we had to deal with run conditions, race conditions. If all the instances start at the same time, how does one become a leader, one doesn't? What do we do with the keys? Where do they get stored? Where don't they? Are we building a new cluster? Are we restoring an existing cluster? Have we had a total cloud outage, provider outage? So we're rebuilding from an existing backup. All this logic we had to be baked into a runtime of the instances as they start up. They need to understand what roles they were performing and whether they're joining existing clusters or not. And we didn't want 101 different versions of our AMIs because that's more work for us to manage. So we baked a lot of knowledge and service discovery as part of the onboarding of each machines. They would inspect themselves, identify what role they were going to perform, and then alter what they were doing. And we built all of this via Packer.
And again, we followed the same principles, right? So everything as code and everything built using a pipeline. So we have pipelines that manage our Packer builds, pipelines that manage our Terraform validations, plans, and applies as well.
So this is a Packer file for a Linux machine. It's in JSON. Okay, it might not be the most readable, but it's there. You can read it, yeah? And you can send it through JQ if you want, or you can, it's there. It's visible to use. But we've integrated this with pipelines. So here are some examples of some pipelines. So the first step we always do is we validate the code. If it's valid, we then move on to a build. And each build then triggers a new image, a new AMI, which we can then utilize later on. Anything else on that one?
Nope. So if we now look at Terraform, so we've used Terraform over CloudFormation just because it's some of the skills that we have. We've done Terraform using modules, so tried to modularize it as much as possible to make it as simple as possible for us to use. We've again built a pipeline around our Terraform that does validation of the syntax. It does a plan so that we can see what changes it would apply. And then we've also got a separate manual run that is an apply. So we actually get the opportunity to view the output from the plan before it does the apply.
Yeah, and here it is. So this is a pipeline. So the first thing we do is we do a validate, we do a plan. And that, for this environment, for the demo, what we did is it automatically flows through to an apply. You don't have to do that. What we would do in reality is we'd have this as a manual step. So you get to a point where you have the plan. Somebody can review the plan and confirm that it does what it needs to do. Then the relevant person, and you can control access as to who can do what within the tool itself, can then authorize the actual apply. So that's why it makes the changes. So you have good visibility of what you're doing. And because everything it's all in code here, and we have known points in time, we can always rerun at the same step, and it will revert the infrastructure back into the same known point in time. So if you think somebody's gone in and made some changes, disgruntled employee, accident, somebody's run the wrong job, put the wrong keys in, you always have the option then to replay back to a known point in time.
So can we go back to the AWS console and see how our instances are doing?
So there you go. So that first one, it looks like it's back up and running. So the Linux machine is back up and running. Let's have a look, see if it's joined the cluster. So the red text there is because the cluster's out of sync. And that's gone away. So we sort, so manager, it's not quite yet joined yet. Oh, it has. Sorry, I couldn't see it. That one's actually, it's on its way back up. So it does take a few seconds, but they are in the state of initializing at the moment, and we can see that in the background here.
So Windows always takes a bit longer than Linux. So we'll take a couple of minutes, but what we can do while that's starting is maybe dig into the dashboards a little bit more.
Sure. Should we do Kibana or Grafana?
So if we have a look at Visualizer, we should see that the instances that have died have gone red.
If I just zoom out a little bit, so you can see they were red. If I refresh, so that was the Windows worker, and the manager is gone off there altogether now. So just go back here and refresh.
The joys of a live demo.
Well, there you go. So we've got 3 managers back up again now. So manager 1, 2, 3, and they're back up and ready in green. And the red error has gone away. So the database, the cluster is back into a healthy state. So on the Windows side, the containers are still large. So whilst the smallest Linux container you get is like 4 meg for an Alpine, on 2016, the smallest Windows container you get is about 15 gig. So it is bigger, but you know it's Windows. You are working Windows. That's the environment you're in. But it's a base limit, so you still get the same LED file system. So the first base image is 15 gig. After that, you then go into the deltas, so you get LED file systems. So it makes it a lot quicker, and it also means you can pack your machines a lot more denser as well, because you're not having to get the same 15 gig base image every single time. All you're doing is putting deltas on top of that. And we've been able to get some quite good utilization out of that as well now. So let's just have a look back onto the dashboard, see if
should be coming out.
Should be there. Windows, it's running. Okay, that's that one, and but they're both up and running. We should see that one having joined up on there. And just to confirm, what we'll do now, if I hit refresh on the app, we should see that it's still working. Yep, so still up and running. No effect to the service. It's taking a while.
So while that last Windows virtual machine is joining the cluster, are there any questions? Because it might just take another couple of minutes. Yep. Or there's a couple.
Mm-hmm. Right, yep. Are we on? You said you're using Docker Enterprise. For those who aren't paying an absolute fortune to Docker, what would we be missing out on that you think we need?
So there are a number of reasons that we've picked Docker Enterprise. So we have a variety of clients who, whilst like the idea of open source, they also like the idea of a fully supported product that's fully supported by a vendor. Docker Enterprise also comes with some additional tooling, so it has the ability that within the orchestrator you can get image scanning within the Docker Trusted Registry, which will do security scanning of the layers within your image. You have things like RBAC built in, rather than having to try and integrate with other third-party providers. So the package you get that is Docker Enterprise has a variety of all that tooling, if you like, that is already built in and closely integrated without the need to do that from multiple suppliers. So Docker have also last year announced the ability that you can now run Kubernetes Workers as well. So more than just Swarm, you can now do Kubernetes. And
for us, the multi-tenanted deployment was key, because it's not just role-based access on what users can do, it's also where they can do that. So you can dedicate workers to certain teams, certain business units, even certain suppliers in a multi-supplier way of working. So they can't interfere. You can give them full admin on those machines, and that's all you can do. So they can't accidentally delete another supplier's code. Okay, and there you go. So our top one there, Windows node is back in, and it's currently pending. It's just waiting for a health check. But that's drawing back the cluster again. So the platform is now healing itself. And that's without us having to do anything other than, well, just wait.
More questions?
Just a quick one. I was wondering what trade-offs you went through that led you not to use Amazon's code build service, for instance, for building your Docker images.
So that's a very good question. So rightly or wrongly, we have a variety of clients who like the idea of being cloud agnostic. So they want solutions that can run in either AWS or Azure. So there is often a push to use more tooling that would cover both multiple cloud vendors and a simple solution that would cover multiple cloud vendors rather than going all in with a single supplier. So whilst there's nothing here that you couldn't do using AWS's services themselves, so the registry, code build, code deploy, etc., we've just done something slightly different.
Yeah, and they always have ambitions to stay cloud agnostic to a point as well. So this gives us that. So the pipelines, if they wanted to lift and shift this back onto on-prem or move across to another cloud provider, they have the ability to do so. Okay, and there you go. So I think it's back up and healthy. Any other questions?
May have time for one more. Very quick one. No, all done. Right, super. Thank you very much.